Okay, so our next talk is two wind interactions in a binary system with two orbiting giant stars with Antonio Castellanos-Ramirez. So please take it away. And I'll give you a 9-minute warning.
Yeah, thanks. Can you hear me?
Yes.
Okay. Well, thanks. I talk about this work we done with some of collaborators from Mexico and France. I am a PhD at the Instituto de Astronomía at UNAM. Well, the principal motivation of this work is the seminal paper of Morona and Huggins in 2006, who presented for first time HST images of AFGL 3068. Can we see these images shown a spiral pattern caused by a three-dimensional shock from the interaction between an AGB wind and a binary companion in almost a circular orbit. As we can see, the observations well fit an Archimedean spiral. There are some other works showing these spiral patterns, arcs, or rings, very similar to this one. There are some of these works. So based on these works, we want to explore 3D gas dynamical simulations of a binary with two red giants for modeling the spiral shock with 1 and 2 strong winds and considering orbital circular orbits. And in the first case, in the case of one single wind, we revisited the analytical model developed by Cantó and collaborators in 1999 and Raga and collaborators in 2011. So I showed some numerical setup. All our simulations share these parameters. That is almost for a powerful wind of an post-AGB kind of. So the first are the mass loss rate, wind terminal velocity, and temperature of the principal wind. All the winds are imposed in a radius of 33 astronomical units. The stellar masses are 3.5 and 3.1 solar masses for the primary and the secondary component. And these are parameters similar to those used by Kim and Tam in 2012, and some kind of parameters like the Morona and Huggins. The stars are in a circular orbit with a period of 130 years. And the binary is initially surrounded by an homogeneous environment with number density of 100 cubic centimeters and a temperature of 50 kelvins. We also include radiative cooling in our simulations. So we want to explore a set mass loss rate and wind velocity for the companion star with these values. Here, eta is the wind ram pressure ratio, and alpha is the wind velocity ratio from the secondary to the primary star. As we can see from the wind ram pressure ratio, the wind of the principal star dominates over the secondary. We have two different physical sizes for simulation. And in the biggest, we explore the full 3D behavior of this phenomena. In the simulation, we just use half of the size of the complete box, but there is no problem here because we can obtain the full 3D simulation by making an appropriate reflection with respect to the orbital plane. Okay, well, now I present some results of our work. In the case of one single stellar wind, this image shows the typical structure of a spiral shock. That is an Archimedean spiral. The red curve in this graph shows the spiral curve predicted by the analytical model. Well, we note that the analytical model and the numerical simulation are in good agreement. This orange circle is the analytical prediction for the locus where the shock structure starts. So that means that inside this the circle, there is a shock-free zone. Now we show the 3D density structure. We see the arc-like morphologies that do not close each other. That means there is a spiral pattern. And well, the shock-free near the orbital axis. We also developed predicted synthetic light, scattered light maps. We do the simplest way. We assume a single isotropic scattering nodose extinction, perfect the dose-gas dynamical coupling, and constant dose-to gas ratio. So we can observe a spiral structure for all of the orientation except for 90 degrees. In this case, we observe separate arcs that breaks close the orbital axis. Oh, my cat is trying to kill me. Okay, well, regarding the two wind cases, as we can see from all these maps, we can observe that a spiral structure has developed in all cases. Notably, we can fit all this by a single or double Archimedean spiral. So this is a result that I don't know is expected, but we obtained this. One feature we observe is that close to the binary, in all cases, we have a double spiral structure. This structure merged into a single spiral at larger distances, except for the model M4, because this is a case where the stars are exactly the same. Another feature that we can observe is the development of instabilities. The thin shell instabilities are responsible for perturbation in models M1b, M2, and M4. For the rest of the models, there is a mix between this thin shell and Kelvin-Helmholtz instabilities. The last are dominant in models with larger velocity differences between the primary and secondary wings. And these perturbations we can observe, for example, in here, or in this model here or here, form clump-like structures. These structures have been observed in some spiral patterns before. So we can see that these structures could be interpreted as evidence for the presence of two winds with a large wind velocity contrast. Okay, now I show the stratification density for model M1C on the XZ and YZ planes. We can observe that there are flow, unperturbed flow here, followed by shock zones in here. So, well, we can see also that the secondary wind that is shown by this contour is constricted, sorry, for a zone near to the, thanks, near to the orbital plane. And the strong wind is confined in almost a conical section, that section here. From our predicted scattering light maps, we observe a clumpy spiral for 0 and 30 degrees. But for 60 degrees, the map shows a morphology of a spiral with a squarish shape. And for 90 degrees, the map shows a stepped biconical structure aligned with the orbital axis. This kind of morphology has been previously observed in some planetary nebula. So we can say that this kind of morphology could be obtained by the interaction of binary systems similar to those presented here. Sorry. Okay, so well, that's all. I left here some of conclusions. Thanks.
Thank you very much. Your cat loves you.
Yeah, it is a quiet little cat, but I don't know why.
You did great.
Yeah.
All right. So questions? Let me check in the. Go ahead, Andreas.
Can we
go
see?
ahead.
Can we see the cat, please?
Now he already slept.
Of course, it's a cat. That's what cats do.
Yeah. But she waits that I start to that I finish to talk.
Yeah.
To sleep, to go to sleep. Yeah.
I have a question.
Yes.
Just about the I was intrigued by the fact that you got the strength of those instabilities were different. Could you just remind me? I didn't quite catch what controlled whether or not the instabilities were forming.
Yeah, well, for example, in these cases, the models M1A, M1C, and M3 are the cases with the velocities are different between the two winds. So we think that these are Kelvin-Helmholtz instabilities. In the other cases, model 1B, M2, and M4, the dominates are the thin shell instabilities.
Right. Okay. Yeah. Well, and the strength of the right for the thin shell, the stronger the cooling, the faster the cooling, relative to some hydro timescale, the more you'd likely get that. Bruce Ballack says, I swear we are seeing the red rectangle in your slide number 10. So he feels this is a good model for the red rectangle.
Yeah, we live in that too. Yeah. So we thought that could be this be the explanation of the formation of these kind of structures. Why not?
All right, very good. If there's no other questions.
No, there is one question.
Tola. Jesus Tola, if I'm pronouncing that correctly.
Yeah. Hello. So these instabilities are only for when you have winds from the two stars, right? When you have only one star with the wind, you have this smooth Archimedean spiral, right?
Yeah, but we found in all cases we can fit this Archimedean spiral for all.
So my question goes in the sense that we've been recently trying to figure out what happens between this very nice spiral shapes and then the ring-like structures that we see in the halos of planetary nebulae. So what we see is that these ring-like structures are messy, and we think it's because of the actual evolution of the central stars, of the wind star, the fast wind stars, and photodionization stabilities. But this seems to suggest that originally in the spiral is already unstable. You know, this is. I said this work. I like it very much, what you just presented.
Yeah, but with kind of certain error, you can fit an Archimedean spiral for all these models with two winds.
And what is the actual mass loss rate, or the order of the mass loss rate of the two stars?
Is more or less, well, I here show you.
Oh, yes.
Yeah.
Carmen also asks if you could summarize the main parameters. I think in particular for the red rectangle model in terms of the second wind, like what were you doing to actually create the red rectangle?
Well, we just prove different values. It's not exactly as the parameters for the red rectangle, because we don't try to obtain this model, but it's almost a model when the ramp pressure ratio for the secondary is kind of the 10% of the primary, and with a velocity ratio for kind of 50%, 15%, more or less.
Okay, great. All right. Well, thank you very much. That was a lovely, lovely talk.